Be right back. Hey Alexis, how's it going?
Going good. How are you?
I'm doing all right. Friday, you know?
Ready for the weekend?
I am very ready for the weekend. Very ready for students to be back in class too. So
Oh yeah, definitely.
it's gonna be good. It's gonna be good. All right. All right, it's 12:30. Let's get rolling. Lord, thank you for bringing us together this afternoon. Thank you for all that you do for us. Pray that you would uh, help everybody to make this transition over the next week. Give us a good weekend. Help us to get some rest and do the things that we need to do to be successful. Help us to hit the ground running next week. Make sure that we are we're focused and we're ready to go. In your name we pray. Amen. Okay. So what are we doing today? Okay, we're gonna do some more stuff. So today, okay. So as per usual, I'm gonna do this, right? So we can all see this now. Axis diagrams and rotating. Okay, so So we haven't done it. Oh, I remember what this is about, right? So we did that problem at the end of class last time where I rotated my axes, right? Why would you want to do that? We showed that it, hopefully you guys ran it the other way and got the same answer, right? But hopefully, what we've shown is that it doesn't matter what you choose as your coordinate system for each free body diagram, right? The numbers will come out the same. So what we did last time was we did that problem with the block, right? There was a block sliding along a block, and the one block had an inclined plane of about 30 degrees. Um, and so we wanted to figure out what is the acceleration of the bottom block, right? Well, in order to do that, you either have to choose your coordinate system to all be in one direction. Can you guys see if I write on that? Yeah. Right. And so we chose our standard XY coordinates, right? That's all well and good. But then Dr. D pulled a trick on everybody. And instead of doing that, for one of them, I angled my coordinates like this, right? Where I said that this was 30 degrees different from, right? This is offset from that coordinate system, but angling it 30 degrees, right? So why did I do that, right? Why did I do that? Do you have to do that, first of all? No, because we did the problem at the very end of class and we set it up and we showed that there are two equivalent methods, right? So do it whatever way you're comfortable with. What this allows us to do here is solve directly for the acceleration that we want. And that's why I did it. How do you know to do it that way? Well, guys, I went to college 15 years ago and I've done a lot of these problems. It's practice, okay? It's practice. So now that you've seen that, maybe you might want to try to employ it in one of your problems for homework or whatever. You don't have to. You can get the right answer, right? Or what you can get to the answer by doing it the way that you normally do it using the same coordinate axes, right? All right. Do you guys have any other questions from last class? All right. Hopefully everybody is done moving in and good to go. Right. We're in the Phoenix area now. We're all ready for Tuesday, or I guess for us for Wednesday next week. I mean, I'm sure you probably have classes on Tuesdays too. If you have to be somewhere in person, remember, I know for the last 6 months, I'm guilty of it too, right? You can roll out of bed 5 minutes before you need to be somewhere, put on, wash your face, put on a nice shirt, and call it a day, right? When you have to be somewhere in person, give yourself a little bit more time to get there, right? Just a little bit. So because I'm not going to see you guys before our next class, we are going to be having class in room 1345 in building 1, room 345. Okay, please show up there during our class time. I know we changed it a couple times. This room is better. This room is better, and it will be good for everybody. I know Logan asked a couple classes ago. I will still plan on taping um, taping the lectures as we go, so you guys can refer back to them later if you want. But I would still recommend taking notes during class and things. I think that why watch a 2-hour video for something that you could just look up in your notes and take a couple minutes, right? Also, it's been shown that writing things down helps you and your brain process that information, right? So good work. All right, so what do we got? Our VAUGT product plans. I talked about this last class. Do you guys have any questions about the VAUGT product plan at all right now? Not really. Look through the rubric, right? Look through the rubric. Make sure to watch the video from the beginning of last lecture to see what all is on there. I pulled all that stuff from LoudCloud though, so it's all in there. We don't have a homework due this week, but we do have one due a week from Sunday, and along with 2 Learn Smarts due a week from Sunday, right? So stay up on that stuff. Okay. So today, we're going to explore alternate coordinate systems, right? So what if we don't want to use Cartesian? What if we don't want to use normal, what we consider to be our normal, I shouldn't use normal. Well, we use a typical Cartesian coordinate system, right? X, Y, and maybe Z, right? If it's 3 dimensions, right? What are the conditions under which we would not want to use this, right? Because I've told you guys, this is an arbitrary choice, right? This is something that you can use whatever coordinate system you want, but certain coordinate systems help you do a problem better than others, right? So let's jump into it, right? We talked about normal and tangential coordinate systems when we did kinematics, right? These are typically used for systems that we have that run on a fixed path, a fixed circular path, right? So an aircraft or a roller coaster both experience large normal forces during turns. Right? We talked a little bit about normal acceleration in the cars on the Texas Motor Speedway, right? We did that thing. We learned about how you could set up a chain of people to squeeze each other's heads to make sure you don't pass out, right? All really scientific and important stuff. Right? So again, you in kinetics, this is our wheelhouse. These are our equations, right? Newton's second law. And for particles, we don't worry about the sum of the torques, right? We'll talk about that when we get to rigid bodies. But for these particular problems with particles, it's the sum of the forces is equal to mass times acceleration. We went through how to find velocity and acceleration for normal and tangential coordinates. I did the whole derivation, right? Remember, I told you on that day that it doesn't, for us, our purposes, we don't need to know how we got there. We just need to know what the punchline is, right? And so here's the punchline. If I have something that is set up in normal and tangential coordinates, check it out. Here it is. This is my mass, right here, my particle. Tangent to it at any point along its path that it's traveling, you can see the curved motion, right? You will have some component that's running tangential to this path and one that's running normal. By normal, I mean back along the radius of curvature, right? So you are, the easiest way of imagining this, right, is also our integrated faith, learning, and works for the day. David swinging his sling around his head, okay? The sling creates a circular path, right? And it is always going to be a circular path of the same length, right? But what happens? If you were to freeze that in time, there is a force pointed in the direction of motion, and there's one pointed back along the string that you're holding, right? Along the sling itself, right? Keeping it in place. And that is typically how we view normal and tangential coordinates, right? So what is that length, right? We'll talk about that in a second. We'll talk about that, right? But so in general, we can rewrite this as the mass times the velocity, the time derivative of the velocity. The tangential acceleration here is just the acceleration that how we're used to seeing it. The normal acceleration is defined as the velocity squared divided by rho, and rho is my radius of curvature. Okay. All right, so that's all well and good. And these are important equations and we need to remember. But how do we use them, right? How do we use them? That's a really good question. Let's use them on this pendulum. Okay. So I have my pendulum. I've got a bob of 2 meters that describes the arc in a circle in the vertical plane. So what is this saying? This is saying that if this were allowed to rotate all the way around, right, it would create a 2-meter radius circle around point O. I realize this is not a very good drawing. But, right, imagine that this, for some reason, can swing through the wall, right? And it comes all the way up. It would create a circle that's got a 2-meter radius, right? So they're telling us that this length here is 2 meters, okay? We know the tension in the cord is 2.5 times the weight of the bob for the position shown. We need to find the velocity and the acceleration of the bob, right? Okay. So how do we do that? Well, what's it asking us for, right? It's asking us for the velocity and the acceleration. Well, at first glance, you'd be like, well, that sounds kind of like a kinematic problem, right? Except that they're giving us forces. And whenever we're given forces, we should try to use Newton's second law. So let's draw a free body diagram for this. Let's draw a free body diagram for this. Here's my free body diagram. I did it before class. I got bored, guys, so I did it before class. Let me move. I think my picture on this video screen is probably right above all this stuff. Trying to move things around. That should help. All right, so what do we have? Looking just at the free body diagram, right? Look, there's my mass. There's my mass. And you very well could do this in XY coordinates, right? But we know that the path is described by a circle, right? What was the radius of that circle? Well, it was 2 meters, right? Well, that is our radius of curvature. I'm going to use normal and tangential, right? Because the normal component will always point along the string, right? In the back towards the center of curvature. I then break this down into normal and tangential components, right? What does that mean, right? So I've still got my weight here, right? I'm going to actually draw my weight in a different color. This is my mass times gravity. In the position shown, right, we had an angle here of 30 degrees. Right, we had an angle here in there of 30 degrees, right? In case we don't remember, let's go back and look at our, right? So most of the problems that we do, there's going to be things that say like, you know, in this position, find the velocity and acceleration, right? We want the instantaneous velocity of this pendulum when the angle is 30 degrees, when it is 30 degrees, okay? So like I said, we can break this down into components, right? So what do I have? I've got mass times gravity times the cosine of 30 degrees and mass times gravity times the sine of 30 degrees, right? Because the angle is this angle in here. That's what I'm using. Yeah. And actually, I'm going to erase all this stuff for a second, and we'll come back up with it. Because I want to draw another picture here really quick. So this is all tilted, right? And it's like, it's freaking us out, man. We don't want it to be tilted. All right, well, what if you drew another free body diagram that looked like that, right? And if you're more comfortable looking at it like this, right? Well, that's mass times gravity. And if that's mass times gravity, well, I can still use normal and tangential components here, right? I'm just going to rotate this. So this is going to be pointing, the weight's still going to be pointing straight down. Well, never mind. So let me redraw it. So the weight's not pointing straight down anymore. Now the tension is pointing straight up, right? But my coordinate system has converted that way. And my mass times gravity is actually this way. Okay. I still have my components. We'll call this mg tangential. Call this one mg normal. This angle in here is 30 degrees. Right, so all I did was rotate it, right? But that sometimes helps with visualizing what's going on, wouldn't it? Oh, maybe I confused you guys more. Who knows? Who knows? I hope I didn't, but could happen. So what is the benefit of drawing it one way versus another? Well, it's all in your head, right? Just making it more comfortable for your head. The the information hasn't changed at all, right? The information hasn't changed. We're just, when you look at this, the idea of coming up with components is nicer when everything is running like a right triangle that's 90 degrees in front of you. I mean, it's the same deal. All right. Did I confuse everybody more by talking about this way? No. More, same, or the less amount of confusion? What's going on? Plus, minus, or equals? Okay. I'm going to run with this first free body diagram because they're both the same, but we'll just to save some room here. All right, so what are we going to do? Now remember, we want to find velocity, that's a v, and acceleration. Okay. We want to find the velocity and acceleration of this. So if I was going to draw my kinetic diagram, I would have my normal acceleration and my tangential acceleration. Okay. So what do we do, right? Well, we've got two equations. We had them on the previous page. We've got the sum of the forces in the normal direction, which is going to be equal to the mass times the normal acceleration. Right? So if we start there, our normal direction is up and down, right? It's in the direction of this right here. In the direction of n. What forces do I have in the n direction? What do I got? Anybody? What forces are in the normal direction? What forces are in the normal direction?
The tension.
Tension, sure. Right, and the tension's going to be positive in the normal direction, right? So that's T. What else do I have in the normal direction? What else?
Would the normal like mass times gravity of the ball itself count?
Yep.
Something other than tension.
Right. The normal component of the weight, right, which we've written here as mg cosine 30, right?
Jillian, what were you saying?
No, I was saying, I said that twice, but I was muted, so.
Okay. And that's equal to what? Well, that's equal to the mass times the acceleration in the normal. Okay. But the problem statement told us something. It told us that the tension is equal to twice the weight, right? So T is equal to 2 times W, which is 2 times mg, right? Because weight is mass times gravity. Was it 2 or 2.5? I think it was 2.5 times, right? 2.5 W. Pretty sure it was 2.5. Let's double check. Yep, 2.5 times. Right there. Okay. So it's 2.5 times gravity or weight, sorry, which is 2.5 times mass times gravity. Okay, we can plug that back in. Right, we can plug that back in. And what do we end up with? Well, if we plug that back in, we'll get 2.5 mass times gravity minus mass times gravity times the cosine of 30 degrees is equal to the mass times the acceleration in the normal direction. Well, look at this. We ran into a problem, right? They never told us what the mass of the pendulum is, right? So how are we supposed to do this? How do we figure out the mass of the pendulum? Do you need it?
No, it cancels out.
Yeah. It's in every term, right? It just goes away. Divide out mass. So it turns out that the mass of the pendulum doesn't affect the normal component of the acceleration. Okay. So we can rewrite this, right? And we'll end up with a sub n is equal to 2.5 minus cosine of 30, right, times gravity. And if you run that through your calculator, you'll end up with 16.03 meters per second squared.
And using that, you can go back and find the mass.
So, Julian, for the mass, if
Well,
you
no,
look at
'cause
the
then it would just-
equation, it's in every term, right? So we can just cancel it. So it doesn't matter. Doesn't matter.
I thought in the top equation where it says I guess yeah, you're right. Taking another look at it.
So this here is a separate equation from, right? So I'm just continuing this one on, right? That's what the arrow thing means.
Okay.
So we started with some of the forces in the normal is equal to mass times the acceleration normal. Then we went down and we summed our mass, our forces, right? So we have tension positive. The normal component of the weight is negative, and that's equal to my mass times my normal acceleration, right? We plug in, we were told in the problem statement that my tension is 2.5 times my weight, which is also 2.5 times mass times gravity, right? Because weight is just mass times gravity. And we plug all of those in, right? 2.5 times mass times gravity minus mass times gravity times cosine of 30 degrees is equal to the mass times the normal acceleration. And so we can cancel our mass. All right, we can cancel the mass everywhere. There's one more component to this. There's one more component to this because it asks us for the acceleration, right? And the acceleration is a vector. So there's actually a normal component and a tangential component. So we have to solve for the tangential component before we're done with that. So we have one more equation here, right? Some of the forces in the tangential direction is mass times the tangential acceleration. Okay. What's my forces? What are my forces in the tangential direction here?
mg sine 30.
There it is, right? mg sine 30. So mg sine of 30 degrees is equal, that's the only force, so that's equal to the mass times the acceleration in the tangential direction. Well, our masses cancel again. Gravity is 9.81 meters per second squared. Sine 30 is 1/2. So 1/2 of that gives us our tangential acceleration being equal to 4.91 meters per second squared. And we're just plugging in here. So if we wanted to write this, right, if you wanted to know what the acceleration is, you would say, I have 4.91 meters per second in the tangential direction and 16.03 meters per second in the normal direction. What if they asked you for the total acceleration? Right? How would we do that? Right? Let's call that a total. Right? Well, remember, a total is just adding these vectors together, and they're 90 degrees apart. So it's just Pythagorean theorem. And that will give you what we call the norm of the vector or the magnitude of the vector. Whenever we're talking about getting magnitudes of vectors, right, which is something that we'll talk about more later on. It's just asking you to use Pythagorean theorem. That's what it is. Okay. So the last part is to find the velocity, right? Find the velocity. Okay. So velocity is equal to what? For this one, we're going to go back a couple slides and we'll talk about it. So let's go back here, right? Look, my normal acceleration here is equal to what? It's equal to my velocity squared divided by rho, right? So if we run off this equation, right, which is one that we derived a few classes ago, right, we can rearrange this, right? We can say that the velocity is the square root of rho times the acceleration in the normal direction. We know rho because we were told what the radius of curvature was for the pendulum. We've just figured out what a sub n was, right? So we should be able to get the velocity, right? So the velocity using that equation should be rho times a sub n square root, which is the square root of 2 times 16.03, which is 5.66 meters per second. Now, is that positive or is that negative, that velocity? And how would we know? What do you guys think? Gut feeling. Let's do it this way. In the chat, write if you think that it's positive or if you think that it's negative. You got a positive. Couple positives.
Is this in regards to the
The
velocity?
velocity. Is the velocity positive or negative? Okay. Got a negative. I got a bunch, mostly positives. Mostly positives. Well, guys, you are all simultaneously right and wrong. Okay. This is a pendulum, right? It's going to hit 30 degrees in either direction, right? So it's actually both positive and negative. It depends on whether we're on the upswing or the downswing. Trick question. Trick question.
'Cause I was thinking if it goes like, hold up, if it goes like this way, so it's going backwards, it'd be going
Right.
negative, right?
So if it was swinging, right? So in this case, if it was swinging to the right, right, you'd have, based on our coordinate system, you'd have negative, Julian, right? But if it was swinging the other way, you'd have positive. So it really depends on a couple things. How did we define our coordinate system? And is it on the upswing or the downswing, right? Which we don't know. So this is actually a plus or minus 5.66. It's plus or minus. All right. Cool. Does have any questions on this one?
So,
Yeah.
I guess I'm still kind of confused as to where the AT, OT, the square root of 8n squared plus AT squared comes from.
For which one? For how we found the velocity, Zach, or how we find the total acceleration?
I guess the velocity.
For the velocity, that equation, this one down here, v is equal to square root of rho an, comes from the kinematics, right? So when we, a long time ago, like 2 weeks ago, we came up with equations for normal and tangential acceleration, right? And it turns out that the normal acceleration is equal to v squared over rho, right? So if I want to solve for the velocity there, it's v squared, right, is equal to rho times an. And so then you take the root and you get square root of rho times an is equal to v. Right? So that comes from when we were doing our kinematics stuff and we talked about normal and tangential coordinates. That's where that comes from. So we don't need to go through the derivation. I don't think that it's important for this class, but I do think that we need to understand that when you see normal acceleration, you should think v squared over rho, right? This is going to come up a couple. This is going to come up, right? Because it's an easy way for us to figure out velocity by finding normal acceleration. That answer your question?
I think so, yeah. I
Okay.
was just confused at first as to how that related to the equation.
All right, this here, that one is a four-year information. We'll touch on that multiple times coming up. You guys have any other questions? No? All right. Okay. Okay. So we're gonna do this one. Well, you're gonna do this one. I'll throw you in your groups. This one give you. Let's see. We're only gonna do two groups because there's only. Everyone here today? We're only gonna do. We got 8, so we'll do two groups. Okay. I'll assign them randomly. All right. I'm gonna give you guys 45 minutes to work through this problem. 45 minutes. So what do we got? What do we got? All right, I've got this car and it's driving on a banked turn, right? I want to determine the rated speed of a highway curve that has a radius rho, so a radius of curvature of 400 feet, and it's banked through an angle of 18 degrees. The rated speed of a banked highway curve is the speed at which the car should travel if no lateral friction force is to be exerted at the wheels. So when you're drawing your free body diagram, should you include friction or should you not include friction?
No friction.
No friction.
Right? Because this is the worst case scenario, right? You're driving on an icy highway on a banked curve, and you want to make sure that there's no friction, no lateral friction between those wheels. Okay. All right. If you guys can get 45 minutes, I'm opening the rooms. I'll bounce around between them, answer any questions, right? But you guys work through it. We'll go over this when the rest of you get back in here. Right? But imagine for a second you're looking top down. Right? You're looking top down. That's the road. I realize that that is horribly drawn. Right. Here's the road. Okay, here's the road. Here's the car. You know, row. You know, row. If you were looking at this from the top, you'd have tangential, normal, and then y coming towards us, right? And so if we go back and we look at this, go back and we look at this, you'll see that's where this y and this normal force come from. Oops. So like I said, we'll talk more about that when you guys come back in the class. I just realized that I was muted the last time I came back in here. Oops.
I like the glasses. Very stylish.
Thank you. Thank you. All right. Cool. We're all back. Awesome. We didn't get lost in the ether. I always get nervous that somebody's just not gonna make it back from the breakouts, man.
Somebody just disconnects.
So not today. Not today. All right. So we all got there. We all got there. Let's talk about it. All right. So what do I have going on here? Notice they've given you normal and y, and we were talking a lot about normal tangential, right? But I explained this to you guys, but just so it's for posterity and it's in the video, right? Imagine for a second that I've got my highway. Here's my car.
Your screen is like really zoomed in. I don't know if you did that on purpose, but I was just pointing it out. Sorry.
That's weird. It's like really zoomed in on the.
I don't know if it's just me, but
No, it's the same for me as well.
Yeah.
Is anybody else having issues?
I'm seeing like a zoomed in like circle with like a red tiny square in it.
Yeah, that's yeah. We're just in the top corner.
Yeah.
Yeah, that's all we're going with right now. All right. So we've got some row, right? Get some row here. We know that that's 400 feet for us, right? So we're at 400 feet. And if we're doing this, right, our normal and tangential coordinates would look something like this. And we would have our vertical coordinate y coming out towards us, right? So when we go to draw this way, right, where this is 18 degrees, here's my car, right? My car, I've got my normal force here. They call it R in the picture, but this is just my normal force, right? And we know that that's at 90 degrees, right? So there's that. And we've got our weight here. Our weight is going to be like that, right? And our coordinate system that they gave us was, hey, here's normal and here's y. All right. So we can draw components of this, right? And we'll call this n in the normal direction, and we'll call this n in the y direction, right? N in the normal and n in the y. And so that makes what? That makes this angle up here 18 degrees. That's what that makes that. Okay. Remember, what were we being asked to find, right? We want to find the velocity of the car. That's the tangential velocity, right? The forward velocity. Okay. Okay. So far, so good, right? We've got our free body diagram. Could we draw a kinetic diagram? Sure. Why don't we do that just to ensure that we know which way the velocity, the accelerations are going, right? So this free body diagram is going to equal this kinetic diagram. And I know what you're thinking. That's a serious car. Where can I buy that car? Well, Tesla's going to be coming out with it soon, so it's fine. So they bought this design from me. What do we have? We've got the mass times the acceleration normal, and the mass times the acceleration in the y. And hopefully you can read that, right? But they're just pointed along the axes, right, in the positive direction, because we're going to assume that they're moving positive, and if they come out negative, then we know that we chose wrong. Okay. So what? So what do we do now? Well, I'm going to choose to sum my forces in the y direction, because remember, we don't know any other way of doing problems yet, right? We only know Newton's law for kinetics problems. That's it. And because we don't know any other way of doing these problems, we're going to use Newton's law. We have two axes, right? We've got normal and y. So we can sum our forces in each direction. So what forces do I have in the y direction here? So the sum of the forces equal to the mass times acceleration in the y. What are my forces in the y? What do I have?
Gravity and normal.
Gravity and normal. Weight is completely in the y direction, and I have the y component of my normal, right? And that's going to equal the mass times the acceleration in the y. But we did a couple of problems like this on Tuesday, right, where we were sliding on the ground. And if we're sliding on the ground, are we expecting that we will have any y direction acceleration? Are we going to be leaving the ground?
That should be 0.
Should be 0, right? We're not, it doesn't say anywhere that we are hitting a sick jump, right? This isn't the General Lee. For those of you who don't know what the General Lee is, it's from the Dukes of Hazzard. For those of you who don't know what the Dukes of Hazzard is, you're probably better off anyway. All right. So we're left with this, right? We're left with this. But we also know that the y component of our normal force is just going to be normal force times cosine of 18 degrees. And that has to equal my weight. Okay. That doesn't look super helpful right now, right? That doesn't look super helpful, but we're going to keep that. I'm going to call this equation 1 for right now. And I'm going to shift and start talking about my normal direction forces and how they're equal to the mass times the normal acceleration. And my mass times my normal acceleration here is, that's what we're going to be looking for. We're going to look for the normal acceleration, because remember, the normal acceleration is equal to v squared over rho. All right, so what are we going to do here now? Well, I have to figure out my normal direction forces. Well, I've only got one, right? I've got my n in the normal, and that has to equal the mass times acceleration in the normal. Okay. Well, n in the normal is n sine of 18 degrees, which is equal to mass times v squared over rho. Okay. Well, I've got two equations, and I've got three unknowns. Right? That's a problem, isn't it? Well, kind of. Kind of. I'm going to solve equation 1 for n, right? So solve 1 for n. And what will you get? You'll get n is equal to the weight, right? But weight is just mass times gravity. So let me say that. Well, the mass times gravity divided by cosine of 18 degrees. And I'm going to plug this into equation 2. mg sine 18 divided by cosine of 18 degrees is equal to the mass times the velocity squared over rho. Well, check this out. My masses cancel. Turns out that it has nothing to do with the mass of the car. This is good for any car. You could have a Cybertruck, right? Or you could have a Prius, right? And this would be the same for anything, regardless of what the mass is. 18-wheeler doesn't matter. Okay. Sine over cosine of the same angle is tangent. Right? Sine over cosine of the same angle is tangent. I can rewrite this. I can say that V is equal to rho times gravity times the tangent of 18 degrees square root. And if you solve this with your variables, right, which are 400 feet and 32.2 feet per second squared, for English units, right, you will get 64.69 feet per second squared, feet per second, not squared, feet per second. which is approximately 44 miles per hour. So what does that mean for us? That means that the fastest that you want to go before you'll start sliding out is 44 miles per hour. That's what that means. Before you start to see weird normal accelerations. Remember, this is rho up here. Rho is 400, so let's just write this. Square root of 400 times 32.2 times the tangent of 18 degrees. Now, some of you did it in SI units, and that's fine too, right? You convert that 400 to meters, you use 9.81 meters per second squared, multiply by tangent of 18 degrees. Make sure your calculator is in degrees if you're using degrees, right? That's the other thing. Okay. Does have any questions on this one? Normal.
Can the N almost be seen as a kind of like the X direction, sort of?
If it
Not the
helps-
normal force, but like the when you say like F
Yeah.
of N.
So, Zach, if it helps you to think about it that way for this problem, I mean, it's the same relationship, right? The only thing that's different about it is the fact that because it's a normal acceleration, we know that it has to be equal to v squared over rho, right? That's what makes it different. If you're looking at it here, right, normal and tangential, I mean, it's all coordinate systems that we use are going to be 90 degrees to one another, right? It's what we call them orthogonal coordinate systems. So every coordinate system that we use has that property, right? So whether you're using X, Y, Z or normal tangent Y, right? Like it's the same thing. So if it helps you to think about this, instead of calling it normal, to call it X, right? In order to get the math done, that's fine. But you have to remember that it is normal. And because it's normal, it's special because it allows us to calculate this normal acceleration, which is the key, right? That normal acceleration, that's the reason why this coordinate system is useful. Because if you can calculate normal acceleration, you can figure out what the velocity is without having to figure out any derivatives for your stuff, right? For your equation. Stuff is a technical term, by the way. So you guys have any other questions? It's getting a little dark in here. I'm taking my glasses off. No? Is there anything else?
Better understanding of it now. Of like the
Sorry,
whole...
Julian. I'm having trouble hearing you today.
I think everyone has trouble hearing me every day.
So what's up?
But yeah, no, it's just yeah, like you drawing out the whole like curve part really helped. Like figuring out how why the normal was on the left.
It's sometimes like I get it. Like this is the first time that we're seeing some of this stuff, right? And so again, I've done a lot of problems, right? I've done a lot of problems, and you guys haven't yet. So some of it comes down to practice, and some of it comes down to seeing things, right? And just
These problems take a lot out of you, like when you're learning them. I'm not gonna lie.
we got anything else? Any other questions? No. Let's try another one then. We'll do this one together. Do this one together. Here's another one. All right, so what's this thing? Well, I've got a 3 kilogram collar. This B is a 3 kilogram collar that rests on a frictionless arm that we're going to call A prime, right? So from A to A prime here, it's a frictionless arm, so the collar can slide, right? The collar is held in place by a rope that's attached to the drum D and rotates about 0.0. The linear velocity of the collar is increasing according to the equation 0.2 t squared, where V is in meters per second and T is in seconds. Find the tension in the rope and the force of the bar on the collar after 5 seconds. All right, so we need to find the tension in the rope and the force on the bar. All right, so imagine for a second, this thing's already, you walk into the room and this thing's already spinning. It's sitting on top of a table, right? It's spinning around. We're looking at it top down right now. We're looking at it top down. And it's just spinning around, it's spinning around. And because it's already at steady state and spinning, that mass B is out all the way as far as it can be, right? Some distance R. And so there's some tension in that rope that's holding it in place, right? We can all kind of maybe imagine something like that happening. I don't know why this would just be spinning like that, but that's fine. We don't need to know why. We just need to know that it's there, right? Maybe it's the saw house and you need to figure out how, I don't know, you need to figure this out.
It's the doohickey.
All right, so what do, right? Well, we got to start with our free body diagram here, right? So let's redraw this, and I'm just going to draw the collar here, right? So it's my free body diagram, and I'm just going to draw the collar. Right, if I cut this collar, what do I have here? Right, so I'm taking the bar out, I just have the collar. Well, in that case, I'll have some tension, right? That tension is going to be pulling back on this, right? It's pulling this back to center. That's my tension. But I also have a normal force. And what does this normal force do to? Well, remember, this is a donut-shaped collar that's sitting on a bar, right? So if we were looking at it head on, right, you'd have something that looks like this, right? And there would be a bar in here. But we're drawing the free body diagram, so we remove the bar. So that contact between the bar and the collar is what we're modeling as this normal force, okay? All right. So we've got tension from the cord, right? We've got a normal force there. I'm going to go ahead and say that there's some angle theta here, right? What else do we know? Well, we need to decide on a coordinate system, right? But before we do that, I'm just going to go ahead and draw this collar here because we're going to need a KD for this. Okay. Which coordinate system do you guys think we should use for something like this? It's just, we know that it's a constant circular path that we're traveling around. That distance won't change, right? That distance R is constant. So what do you guys think? Which coordinate system should we be using here?
Just a normal XY.
Do we want to use normal, like it's typical XY?
Or we could use the T and N as our coordinate system.
So we're gonna use normal tangential, right? Because here's why. ECT. Right. Our forces are already in line with that, right? And no matter what position I pick this at, no matter what angle this is at, those forces, that normal force is always, and this is where it's tricky, right? Because the normal force is actually tangential to this system. And the tension is normal, right? The tension is pulling it back towards the center of rotation. Okay. So if that's the case, then I've got mass times acceleration tangential and mass times acceleration normal, right? It's my KD. I drew those in the wrong direction. I apologize. Whoa, what the heck happened there? Okay, I'll just redraw the whole thing. Mass times acceleration normal and mass times acceleration tangential. Okay. We have a couple things that we were told, right? So I'll write down my knowns up here. We know that the velocity is described as 0.2 t squared. I know that r is equal to rho is equal to 0.4 meters.
Are you writing something on the screen?
Yeah, did you guys not see anything that I just wrote down?
It's not. Yeah, it's not updated.
How about this? Does that work now?
There we go. Yeah,
Sorry,
that's
I had I paused the screen share for some reason, for reasons, and then the world collapsed, I guess. Okay. So V is equal to 0.2 t squared, R is equal to rho is equal to 0.4 meters. All right, these are all things that were in the problem statement, right? Those were on the problem statement. So what else? What can we do now? Well, you know what? I will also write down that G is equal to 9.81 meters per second squared in case it comes up. I mean, I don't know for sure if it's going to come up, but why don't we start writing that down just so we don't accidentally use 32.2 when we shouldn't, right? Just to remind ourselves, always check those units, right? We know this has to be meters per second. Okay, so let's look at our equations, right? What if I want to sum, I'm going to sum my forces in the tangential direction. That should equal mass times the acceleration in the tangential direction. Well, these forces are perpendicular to one another, right? So we have there's no components that we have to deal with. We don't need to know what angle that is. This is just going to be equal to n. And on the surface, that doesn't look overwhelmingly helpful. I know. It doesn't. But we're going to hang on to this for a second. We're going to hang on to this for a second. Let's look at the normal direction. What should be equal to mass times acceleration in the normal direction. Well, again, we only have the tension. That's it. All right, so everybody's with me so far, right? We're just summing our forces in the directions that we have. We have the normal force in the tangential direction. We have the tension in the normal direction, right? Is everybody all right so far? We following, we tracking. Okay. All right, so like I said, this seems weird, right? Because I don't have enough, right? They didn't tell me anything about the accelerations. How am I supposed to go about this? I want to show you guys something that we talked about earlier. I want to show you guys something we talked about a few slides ago. If I can get there, I have to go very slowly. I want you guys to look at this. Notice these equations, right? The first one on the left is the sum of the forces tangential is equal to the mass times the tangential acceleration. The second one is that the sum of the forces tangential is equal to mass times the derivative of the velocity with respect to time. That's interesting, right? That's interesting. Let's think about that for a second. Can we exploit that relationship at all for this? Well,
Well, we have V, so we could find the derivative of V.
Yep.
To get the
Exactly.
acceleration.
So if we take the derivative of v, right? So let's go back up here, right? So I can write this as m dv dt, right? Is equal to my normal force. I know the mass, right? We were told that the mass was 3 kilograms, right? And let me put that under my knowns as well. 3 kilograms. I know the mass. I know the velocity equation. I can take the derivative of that, right? So what's the derivative of v here? What's the derivative of v?
Acceleration.
Yes, it's acceleration, but like in the less, like this v right here. Right, what's the derivative of 0.2 t squared? In the less abstract, like not the metaphysics of it.
0.4 t.
Yeah, 0.4 t, right? Three times 0.4 t is equal to n. And the problem statement said to analyze this at 5 seconds. So if I plug in 5 seconds, I get 6 newtons. Okay. Nice. Right? So that's cool. What about, so that's half of it, right? Because we're asked to find the normal force and the tension. So how do we find the tension? Well, we have to exploit our other relationship here, right? V squared over rho is equal to T. Again, we know M, that's 3 kilograms. We know V, that's 0.2 T squared. That whole thing is going to be squared again, though, right? Because it's V squared. We know rho. Right, we can plug some things in. So we'll have 3 times 0.2 times 5 squared, whole thing squared, divided by 0.4 is equal to T, which is equal to 187.5. Right, so this one we had to think a little bit outside of the box, right? We had to go back to what is actually our tangential acceleration. What actually is our tangential acceleration? How do we determine that from our velocity, right? I'll clean this up for a sec. 0.2. I'm going to make that look nicer because it's bugging me. 0.2 times 5 squared. There. I like that better. It looks a little better. Okay. You guys have any questions on this one? So again, we can exploit normal and tangential coordinate systems to get direct relationships for velocities, right? Or we can exploit what we know about velocities to figure out forces by using normal and tangential coordinate systems. Okay. All right. Well, okay. You guys have any questions on that before we move on to radial and transverse coordinates? I do want to make sure we at least get to I have a sweet video today. I swear. It is. It's a crowd favorite. Okay. It's a crowd favorite. All right. So if nobody's got any questions, we'll move to radial and transverse. All right, so remember, when we're talking about radial and transverse, we're talking about things like hydraulic actuators, extending robotic arms, and centrifuges, right, that we can analyze. And what makes something a better candidate for radial and transverse as opposed to normal and tangential, right? Well, the difference is this, that the radius here is not fixed, okay? This R in normal and tangential, R is equal to rho, right? And R is not changing with time. In radial and transverse, R is not constant. It can change as a function of time, okay? It can change as a function of time. So how do we do that? Well, here's the equations, right? Here's the punchline. And these are, these are fun equations, right? Mass times the acceleration in the radial direction is equal to the mass times r double dot minus r theta dot squared, right? So what is this saying? This is saying that in the radial direction, we have a component of our acceleration that is due to how we are moving along the radius, but also how our angular velocity is moving. That's what theta dot is. What is this saying in the other direction, right? Ma theta, right? So in the transverse direction, our acceleration is a function of the angular acceleration and the linear and angular velocities here. Okay, and it gets, I mean, that's a messy equation, right? That's a messy equation. So how do we manipulate some of this, right? We'll get to that in a sec. And we're going to do a problem that I'm sure everyone's going to really enjoy. All right, we also call this polar coordinates, right? We call this polar coordinates. If this is in 3 dimensions, we call it cylindrical coordinates, right? We're just doing polar coordinates. All right. So what? So we're going to do this one together. And this one is a problem that students do not like to do. Why is P also called M? All right, Zach, let's look. Because there's some mass at point P. It's just telling you that this particle has a mass M. That's it. Think of it this way too, right? It's a particle that's on a path, right? So that path has multiple points on it, right? So we're saying that that particle, for some reason, if we wanted to, we call it particle M is that point P on the curve, right? So, but it's really just there to show you that that particle has mass. That's what it's there for. All right, so let's try this. And this looks very similar to the problem that we just did, right? With the collar, right? Look, we've got a collar. It's a block sliding on this thing. There's an end stop here, right, at A. So it doesn't fly off. Why? Because as I swing this radially, right, or as I rotate this, it's going to want to push that mass out, right? And there's no rope connected to it. So this distance R can change, right? It can change as a function of time depending on how fast I'm spinning this. Yeah? And that's the difference between the last problem and this one. And that's the key difference, right? That's the key difference. Because if this was locked in place, then, right, once this gets to the end, if you're spinning this around and that's at the end stop, we're using normal tangential, right? That's not moving anymore. If it is in transit to that point, this R distance will change. So how do we deal with this, right? So what do we've got going on? We've got a block B of mass M that can slide freely on a frictionless arm, OA, which rotates in the horizontal plane at a constant rate. Now, you're told it rotates in the horizontal plane. Why do they tell you that? Does it matter? It absolutely does matter, because we are looking top down at this now, and imagine that it's on a table and it's spinning around on the table, right? Why is that important? Well, it's the same reason that it's important the last time we talked about something spinning in the horizontal plane. The weight is an out of plane force. So we do not have to include the weight of the object when we are talking about this, right? All right, So knowing that B is released at some distance R not from O, express as a function of R, A, the component velocity, and B, the magnitude of the horizontal force exerted on B by the arm. All right, so basically we're going to do this whole thing symbolically, and we're going to do it together. Okay, we're going to do it together. All right, so what's the first thing that we need to do, right? So what kind of problem is this, right? What kind of problem is this? Well, it's still a Newton's law problem, right? So eventually we're going to get beyond that, but for right now, this is a Newton's second law problem, all right? What coordinates should we use for this, do you guys think? Should we use radial and transverse, or should we use normal and tangential? I'll give you those choices. What do you guys think? Come on. Normal tangential or radial transverse? I just went on a big tear about the difference between this problem and the last one. Which coordinate system should we use? All right, so let's talk about context clues then, all right? Which coordinate system did we literally just introduce and write equations for the slide before this?
Radial and transverse.
It's radial and transverse. Why is it radial and transverse though? And how should we know how to recognize it? Well, we know to recognize it because R, this distance R, is changing. If that distance R is not constant, right, you should be using radial and transverse. Normal and tangential is only good if we know that R is a constant and we call it rho, right? Think about how this works. If we started this down here and we started to spin it this way, right, it's going to start pushing out. And after some time, it will hit the end, right? And it'll stop moving. But while it's moving, right, while it's spinning, there's some time before it ramps up to steady state. And in that time, we are going to want to know how can we describe the motion of this block on its way to the end stop, right? So if we draw a free body diagram of our block here, it would look something like that. Here's point O down here, right? We're going to say that this distance from here to here is known as R. R is changing. It's not fixed. This is block B. We have some force here that we're going to call F. What is that force? Here's my velocities in this direction. My coordinate system. I've got my radial coordinate in the direction of motion and my transverse in the direction that my angle is changing. If I drew this here, this would be theta, right? And theta is changing, we're told, in this direction. Okay. So this one's going to get funky. It's going to get funky. And it's everybody's favorite because there's no numbers. And I know that you guys hate numbers when doing problems. So I thought, you know, this would be a great time for us to do this. So what am I going to have? Well, I'm not sure which direction this is going to move. I'm pretty sure. But I'll write it like that, my KD. And these are equal. Alrighty. So what do we have going on here, right? Is everybody okay with the free body diagram and the kinetic diagram? What is that force F? That's the reaction between the block and the bar, right? That That block is sitting on a bar. And that bar is pushing on the block. And the block is pushing back on the bar. Right, that is the force. Notice I wrote it up here, right? This guy. What do those lines around it mean? That means the magnitude of the force. So we're not concerned with the direction of the force. We just want to know how much total force do we have. And we want it as a function of r. We want both of these things as a function of r. All right, so where do we even start, right? Same place we always do. We have a free body diagram. I'm going to sum my forces in the radial direction. That's equal to mass times my acceleration in the radial direction. What are my forces in the radial direction? Guys, what are my forces in the radial direction? What forces do I have in the radial direction? Okay. What forces? I'm on TV now, so you guys will pay attention, right? Forces do we have in the radial direction? Anybody? Bueller.
VR.
VR. So this is just telling me that the velocity is traveling in that direction. So that's not a force, right? So technically, we should probably leave that off there, right? It's just moving in that direction. That's all we were saying. Another way, sometimes you might see this as like drawn this way, right? This is the direction that R is changing. But yeah. So all right, if I get rid of
Was
that, so we're
was
not
there
confused. What do we have?
M of AR. Or I don't know if
Well, M
that's
of
right.
AR is
MAR.
our inertial term, right? Do we have any forces in that direction along R?
no, because it's able to slide back and forth.
Right. So that's 0. No forces. This is just going to equal MAR. 0 is equal to MAR. Okay. Now that seems like it's not helpful, but let's go with this, right? We know from a couple of slides ago that AR was just R double dot minus R theta dot squared. Okay. I hope I left myself enough slides for this one, right? Okay, so that seems unhelpful. Yes? Okay. It does seem unhelpful. But let's talk about this, right? R double dot, right? That's just my velocity dot, right? I can change the acceleration is the second derivative of the position, but it's also the first derivative of R, right? The first derivative of the velocity. Okay. Well, isn't that just dvr dt? Sure. And here's the part where you're going to be like, Dr. D, you can't do that. But then I'll tell you, well, sure I can, because that's the chain rule, right? I can rewrite this like this, and I can recombine things as VR d VR dr. Now you're like, how, what, say what? Right? That's, I can hear it. I can hear it through the internet, man.
You're blowing my mind.
I know. It's black magic. Black magic. Oh, I'll work on that. I'll work on that, guys. We'll figure it out next time.
So it's derivative of VR with respect to R?
Yes. So the velocity changes as a function of where we are on the bar. Okay. Okay. Now here's so if I take the integral now from 0 to VR of VR dVr. Okay. I can set that equal. Well, all right. Before we do that, why are we doing that? All right. Let's plug that back in for R double dot, right? And so if I'm up here, I bring this back up here and I'm going to plug this into R double dot, okay? Well, if I do that, I can divide through by M. If I divide through by M, I'll get 0 divided by M is 0, and I'll be left with just R double dot minus R, right? So I can say that 0 is equal to R double dot minus R theta dot squared, right? Yeah. And then I can come down here and I can say, well, that just means that R double dot is equal to R theta dot squared, right? Everybody following me on that, right? We're just solving this 0 is equal to MAR equation and reducing it down. So now I have an expression for R double dot that I'm going to plug in. Instead of plugging it in there, why don't we plug it in here? Okay. So I end up with VR dVr dr is equal to R theta dot squared, right? But I'm going to multiply through by this, and I'm going to take the integral. VR dVr is equal to R theta dot squared dr, integral from 0 to R. Okay. And if you do that, right, if you do that, you end up with VR squared is equal to theta naught squared R squared minus R naught squared. So hey, look, it's part A. Ish. Right, I've got an expression for VR as a function of R. I did it. Yay. Right, and so what is this, right? What is this really? This is us using calculus, right? It's us using calculus and rearranging our equations so that we can get one thing in terms of another. Now, I'm going to level with you guys. After today, we are probably not going, well, not probably. I don't plan on having you guys do another problem like this after today. Okay.
I'll be the first one to say thank you.
But I do think it's important to see, right, this especially, the use of the chain rule right here. Okay. Right. This is an actual, like we went over it when we went over integration and derivatives on day one, right? This is one of the rules, and this is perfectly legal. I know it feels like black market math, right? It feels like you're cheating, but you're not. It's perfectly legal. Okay. So the next thing, what do we do next, right? What do we do next? Because we need part B. We need the magnitude of the force. Nope, too far. All right, so the magnitude of the force, right? So for this, we're going to sum our forces in the transverse direction. That's equal to mass times acceleration transverse. Okay. So in the transverse direction, remember, we only had one force in here. That's going to be F. And that's equal to M. And A theta, we can pull up from our notes. Looks like this, right? So what do we do? Well, it's R theta double dot, not R theta dot. I apologize. Sorry. Okay. All right, so follow me on this one, right? We were told that this spins at a constant rate, right? In the problem statement. So if it's spinning at a constant angular velocity, then the angular acceleration should just be 0, right? So we can get rid of that theta double dot. Okay, so we'll have F is equal to M. Let me write it this way. 2m r dot theta dot. Okay, but isn't r dot just v sub r? And don't we have an expression for v sub r squared that we just came up with? We sure do. So we're going to plug that in for v sub r.
I'm sorry, where did that come from?
So remember, we came up with v sub r squared is equal to theta naught squared times r squared minus r naught squared, right? So let me, don't do it. Thank you. So we came up with v sub r squared is equal to theta naught squared r squared minus r naught squared, right? That's what we came up with on the previous,
Right.
for the previous part, right? So if I take the square root of this, VR is just the square root of theta naught squared r minus r naught squared, right? Yeah. Just taking the square root of that. And then I'm going to take this equation and I'll plug it in right here. All right, so let's make that clear. That is v sub r. This is v sub r. As I was just looking at it, I apologize. There should be a dot over this theta naught in all of these equations. It's not just theta. I left it off by accident. I apologize. That should be theta dot. Okay, so we're basically done, right? Except that there's one more thing we can do here. What's the square root of something? What's the square root of that in there, right? Well, the square root of this v sub r term, right? Can't I break this down as the square root of theta dot naught squared times the square root of r minus r naught? These two things are squared in here, right? Can I break that down like that? The answer is yes. I can break that down like that. Which gives us what? Well, that's going to give us theta dot naught times the square root of r squared minus r naught squared times theta dot naught. So the force is equal to 2m theta dot naught squared, square root of r squared minus r naught squared. Fiend. Obviously. All right, so what I want you to take away from this, right? We can do calculus to do this. But the other thing is this, the force, right? The amount of force that is being produced on the block by the bar from this spinning is a function of the initial angular velocity and how far we have traveled from our initial position. And let's think about that. Does that make physical sense with what we know? So this is saying that the faster I spin this, the more force will be generated on the block. That makes sense to me. Does it make sense to you guys? Right? It's also saying that if I was spinning this at a constant speed, the further away I got from the origin of the bar, the more force would be exerted. Right? That seems to make sense as well. So physically, this is confirming for us that the further away we are from the center and the faster we're moving, the more force we will have. Okay. I know that was math heavy. All right. I know. We've
Like, how
got
do you even look at that and just make sense of it? I mean, like
so
from someone who just looks at this at the end and didn't really do any of the work. I mean, like, where would you find that out just by looking at it?
what do you mean, like that the force is? All right, hold on. Let me go back.
Like, how would you come to that conclusion by just looking at the final answer?
Looking at the equation. So if you're just looking at this force equation, right? Theta dot, right? So another way of writing this, theta dot is the angular velocity, right?
Yeah.
So we can write it like this. So if you're looking at this and you're thinking, like, what things, like from a design standpoint, right? I want to hit a certain force, or I need to be below a certain force, right, on this block, right? Because you take materials and you find out that this material is not really great, right, for beyond a certain force level, right? Okay. Well, if you're looking at this, theta dot is just omega. So omega is our angular velocity, right? And so if you're looking at this, you're saying, well, the most important thing here in this equation is actually the angular velocity. Well, how do I know that? Well, it's because it's squared, right? So it's going to increase at a much faster rate, and this omega will get larger faster than any of the other terms in here, right? Because this gets squared every time that we put something in, right? So, if omega was 10, but if the position is also 10, this is getting reduced by a square root every time that you go through this equation, right? So no matter this difference in distance has to be significantly larger than the angular velocity in order for this position to become more dominant than that, right? So basically, because it's squared, it's more important, right? That's why. Well, how do you know that? Cool. We're going to talk a little bit about angular momentum now, right? So this first part is where you guys are going to look at me cross-eyed, and then we're going to watch a fun video at the end, and then we'll be done. We'll do work of a force and work and energy starting next week. All right, so why do we care about angular momentum of a particle? Well, because satellites orbit the Earth, and as we'll find out, there's certain things that we can do that actually help our force analysis, right? So here's our radial and here's our transverse coordinates again, right? Our polar coordinates, right? We talked about this a little bit already. But if I wanted to talk about this in terms of angular momentum, capital H is in our class what we're going to use to talk about angular momentum. And angular momentum about a point O is equal to mass times the radius squared times theta dot, right? Which is the angular velocity, right? Remember, we talked about linear momentum, and linear momentum, right? If you took the derivative of linear momentum, you would get force, right? So if you take the derivative of angular momentum, what happens? Well, here it's showing you what happens. If you take the derivative of angular momentum, you will get the radial or the transverse forces here, right? You will figure out the transverse forces. Well, that's neat. And actually what it is you find out the torques. You actually end up finding out the torques on a system by taking the derivative of angular momentum. We'll talk more about that when we get to rigid bodies. All right, so here's some cross product math that we're not going to worry about. Okay, sound good? Okay. We'll touch on cross products again when we get there, but I don't think that this is value added right now. So from Newton's second law, the sum of the moments about O of a force acting on a particle is equal to the rate of change, right? So we just talked about that, right? The derivative with respect to time of my angular momentum is equal to the sum of my moments or the sum of my torques, right? Angular momentum can be conserved, and when only force acting on the particle is directed toward or away a fixed point, then we're moving under a central force. All right, we don't really need much of this. We're going to keep going. All right, some more vocab, right? Radius vector, OP, sweeps infinitesimally small areas, right? dA is equal to 1/2 r squared d naught, d theta. So basically, if you're talking about like how radar works, right? It sweeps an area. You can get the area that it's going to sweep by this, right? Or we can talk about it as aerial velocity. So how much area do we cover in a certain amount of time? Yeah. We don't need that. We're not going to see that. Okay, good. We're at the video. The video is the important thing. Let me make sure that I've shared my sound. Okay. You guys ready? This is gonna change your life right now. I swear. This is how I really hyped this one up. All right, anyway, let's stop.
M times V, just a little momentum. M times V, just a little momentum. M times V, just a little momentum. M times V. So there you go. That's momentum. And it's your favorite, right? Because it's got a song. But this is angular momentum. It's an L. Yeah, I guess for the same reason as P is linear momentum. Okay, I'm going to try to figure out what angular momentum could be, and I guess it's going to depend on the angular analog to mass, which is, well, let's see, this is linear mass. I guess rotational mass is that thing called moment of inertia, and the angular analog to velocity is omega. Angular velocity. Okay, so we've defined angular momentum, and that's what it is. And look at these units. It's got units of, let's see, the units of L are, the units of the moment of inertia. That's mass times distance square, right? So we've got kilogram meters square, and then we're dividing by seconds. Kilogram meters square per second. Interesting. And the units of linear momentum, the units of P, are just kilogram meters per second. Kilogram meters square per second versus kilogram meters per second. Okay, all right, that's fine. Now, I want to look a little bit more about this L. Let's see what we've got for L. Since L is I times omega, we know that for something that's moving in a circle over here, something that's moving in a circle and attached, that circle is attached, the thing, what do we want? Yeah, a severed hand, actually. Here we go. Let's put this severed hand over here. And it's dried up a little bit too. That's kind of gross. But it is tied to a string, and somebody's swinging it around with a nice live hand over here. And it's going around in a circle. So we could define this distance to be r, and we've got some velocity there, v. What do you want to say? This direction? Yeah, we'll say it's going in a positive direction. That's tangential speed, that direction. And it's got some mass. The severed hand has mass m. So I want to think about what the angular momentum of this thing might be. So we could look at its moment of inertia, and so because, because it is just a mass at a distance r away from the middle, the moment of inertia will simply be m times that r square, and then we have to multiply it by the angular momentum of this sucker. Sorry, not the angular velocity of it, which is just v divided by r. V over r, because v is omega times r. So we can solve this for omega and plug it in right there. And then if we expand this a little bit, check this out. This is m times v times r. And if I underline in blue, maybe you can tell me what to do. If I underline in blue, I find that L is P times Ara. Interesting. I'm not going to write any vector symbols on this because it is just a scalar equation. But just like all the other equations, we find that we can get some angular stuff from some linear stuff by simply multiplying by r. Let me remind you of a few of those. We get, let's see, v is omega times r. Oh man, that's getting something linear out of something. Oh man, that's a little bit different. What we're doing, this is a little bit different. We're taking the regular momentum and multiplying it by r to get the angular momentum. Okay, that is what it is because we've just derived it right there. Now, in general, we might not have something going around in a pleasant little circle like that. So I can draw you another circle and define this angle. I think I'll call it theta. So if I define this to be Ara, just as before, I might have a velocity that's not in a circle here. So my velocity could be this direction. That might be the direction of my velocity. I can't even call it tangential velocity. But check this out. There's an angle between R and V, and that angle is theta. And we could also bring this back and make another little triangle here. This is what I would call R perp. R perp right there is the normal distance away. See this right angle right here? It's the normal distance away from the speed. Very much like the arguments that we made for torque. So if we were trying to define angular momentum for this situation, now let me back up here. I really don't like a capital L. I'm going to make it stylish. There we go. Yeah, okay, script capital L. Here's my angular momentum for this. So the battery just died. I want to review the things that I said. I don't think I did anything really earth-shattering, but I want to make sure that you see what I'm doing here. I need to find the angle between Ara and the momentum vector. And the momentum vector is obviously parallel to the velocity vector because it's just a difference of multiplying by mass. So then once we establish that there's this angle between it, and the cross product uses the sine of that angle. What this means is that if you're going this direction, and the axis of rotation is right here, and you're going straight towards it or straight away from it, then you'll have no angular momentum. However, if you're going, the axis of rotation is here, and you're going that way by it, then you will have some angular momentum. You're a distance Ara away from the axis of rotation with your velocity, then you'll get some angular momentum. This is very similar to torque in its structure. I was just doing a little bit more with angular momentum down here. I said angular momentum is the normal distance away from the velocity. So we can say this velocity, if this thing is moving past the axis of rotation at some weird angle, we can just grab the velocity and bring it down here and say if the velocity were at its closest approach to the axis of rotation, that distance away would be r perp. And so I was just going to say that this is r perp times, I could go in red. Yeah, why not stick with red? This is r perp times m times v. Then you don't have to worry about any signs if you put r perp in there. All right, so I wanted to do a couple questions for you, and those are these. Here is my first question. If my axis of rotation is here, and let's pretend I'm on a table or something. I have a block of wood, and I fire a bullet at it. The bullet is going this direction. Will the bullet cause the block of wood, I'm holding this down, remember? Will the bullet cause the block of wood to rotate in a clockwise fashion or a counterclockwise fashion? So is the torque on the system when the bullet crashes into the block of wood, will it be a positive torque or a negative torque? And I think you'll agree that over here, the torque from the crash will be greater than 0 because it will do a counterclockwise rotation. Now that also means that this bullet, bullet has, let's see, what is this thing? This capital L business right here. The angular momentum is greater than 0 before the crash because it's moving on this side of it. But if I had another bullet over here, we'll do this guy in brown. if I had another bullet over here and there's a smaller rope, another bullet over here with the same speed, you would agree, if this is still my axis of rotation, this block of wood, interesting, would get hit. So the torque of the crash, when it gets hit, is going to cause a clockwise rotation of this block of wood. So the torque of the crash is less than 0. And you'd have to admit that this bullet, sorry about my spelling, wow, focus. This bullet has angular momentum less than 0. So it has something to do with its location relative to the center of rotation, the axis of rotation. This one right here has a positive angular momentum. And in fact, regardless of where it is on its path, as it's going this way, it's going to be up here in a little bit. Regardless of where it is in its path, it will always have the same angular momentum. I guess even, angular momentum will be conserved. We'll see that in the next video. But angular momentum is the same regardless of where it is on this path, because our perp is this distance right here. And on this problem, our perp is that distance right there, because that's the closest approach that the bullet ever gets to the axis of rotation. So the angular momentum of the bullet as it goes in this straight line is unchanged. Good. Good. Now, here's the final question. If I have a nasty brown apple, and the apple is moving, it has mass, let's see, mass is, I don't know, 0.15 kilograms, and it's moving at, let's speed things up a little bit, 220 meters per second. What is its angular momentum? Can you do it? Let's see, for angular momentum, we need this equation. For angular momentum, we need r perp times m times v. So there's something missing, r perp. Notice that angular momentum cannot be defined unless we have an axis of rotation. So I could put my axis of rotation over here. Let's do that in pink. And I'm just going to write L for here. The angular momentum, if the axis is here, is what I mean. The angular momentum, if the axis is here, depends on this distance, where I'm going to call that r perp. That would be r perp times m times v. What about if the axis of rotation were over here? What if it were right there? Ooh, what if it were right here? Let's call this location A and this location B. How does the angular momentum of the apple compare if we let the axis of rotation be here or here? Check it out. This is the relevant distance, r perp A, and this is the relevant distance, r perp B. Notice, because we're talking about the normal distance away from the path of the apple is going like this. We are only concerned about the normal distance, so points A and B are the same. We could say the angular momentum at A is, what I mean to say is the angular momentum of the apple, if the axis is at A, would be the same as the angular momentum of the apple if the axis is at B. And that's just going to be r perp comma A times m times v. I hope angular momentum is starting to make sense to you. We'll talk about it more in class.
All right. So we're calling it for today. Sorry for going over. Have a great weekend. Right. If you have any questions, I have office hours right now. Give me a second to break it down in here and then head over to my office. So probably start in about 5 to 10 minutes if you need me. Make sure you come to class on Tuesday. It'll be nice to actually see everybody. Right now, I'm pretty sure that you're all just floating heads, but that'll either be confirmed or denied on Tuesday when you all make it in person. If I don't see you, have a great weekend. Make sure that you get your stuff done, but also carve out some time to reset your brain. It's important.
Have a good day, Professor.
Take it easy.